Good evening to all of you. First of all, I convey my thanks to Dr. Khuda Bukhsh for giving me this opportunity and introducing him in this platform. So, Dr. Khuda Bukhsh actually currently is a president of postdoctoral scholars at the Mathematical Bioscience Institute as well as the College of Public Health at the OSU State University. He is also a member of Infectious Diseases Institute and has played a crucial role at the present pandemic situation, that is COVID-19 response modeling team, in providing decision analytics support to the Governor's Office and the OSU Department of Health. Before joining the OSU State University, he received his PhD from Technische Universitaet Darmstadt in Germany. His doctoral research focused on mathematical problems in communication network, game theory and other branches in computer science. He holds a Master's of Statistics from Indian Statistical Institute, Kolkata. He is currently interested in applied probability theory and stochastic analysis of biological systems across multiple scales. Besides mathematical epidemiology, he has worked on biomolecular reaction networks and genomics. Today's talk is about the dynamical survival analysis with application to COVID-19. Now I request Dr. Khuda Bukhsh, please start your presentation.
So the crucial question that we begin with is, how do you model an epidemic, or in this case, how do you model a pandemic like COVID-19? Okay, we know a lot about COVID-19 by now, and yet we don't know a lot about COVID-19 because there are a lot of even biological unknowns. So that's the crucial question that we begin with. But before we try to answer this question, I think it's always a good idea to study what people have already done, because this is, I mean, COVID-19 is probably new, but so it's probably a good idea to actually go through a bit of history of infectious disease epidemiology. And as you can see here, in the first point, that this is not new. So even back in the 16th century, particularly by this this person called John Grant, and then 1662. So he came up with bills of mortality records called natural and political observations made up on bills of mortality. So that goes way back into the 16th century, into the 15th century, and so on. So it was already there. So people already started appreciating the fact that, okay, we need to do elaborate bookkeeping of what's happening whenever there is an epidemic and things like that. The first mathematical work was actually done by Daniel Bernoulli. He's not the other Bernoulli who's famous for his probability distribution, but Daniel Bernoulli, he wanted to calculate the increase in life expectancy if smallpox could be eliminated as a cause of disease. So there was a big debate. Back in those days, there were smallpox, and there was big debate whether or not it was actually lethal. It was actually decreasing the overall life expectancy. And as far as I can remember, I think he was probably a lawyer at that point. So he wanted to actually mathematically show that if you could eliminate smallpox, that would increase the life expectancy overall. Then the earliest examples of compartmental models that actually came from public health physicians, not mathematicians. So what are compartmental models? I mean, by now, thanks to COVID-19 and thanks to constant media coverage of COVID-19 and mathematical models, you probably know what compartmental models are. So compartmental models are models that put people in different compartments, like susceptible compartment, people who are susceptible to a particular disease and not yet infected, and the infected compartment, and then recovered compartment. So yeah, these kind of compartmental models were first proposed by public health physicians, actually. And then later, Hamer proposed a mass action model for disease spread in the early as early as 1906. So what are mass action models? Mass action models are inspired by physics, and you might already know physics or physical chemistry as you will. So if you have a chamber of gas molecules, and the gas molecules are moving at random, then the probability that a particular molecule will hit any other molecule is the same. So that's the idea of mass action. And in case of infectious disease epidemiology, what you do is you say, okay, if I'm an infected individual, then I can infect anybody anybody else in the whole population. Like the probability that any two individuals in the population will meet and hence propagate the disease is basically the same. So that's the mass action idea. So it comes from physics. It was proposed by Hamer. And then Ronald Ross was the first to give the notion of basic reproduction number. I'll briefly explain what this number is, but by now I think you are all familiar with this number, basic reproduction number, in the context of malaria. I think it was actually in Calcutta that he did this work. And then came the famous Comet-McKendrick model. They wrote a couple of papers, a series of papers explaining this fairly sophisticated mathematical model of infectious disease epidemiology. They proposed what are known as integral differential equations, so based on renewal theory. And a special case of that model was the ordinary differential equation case, which later became widely used and became kind of the canonical model of infectious disease epidemiology. So yeah, and here this nice review paper by Fred Brower covers all of these materials. So in case anybody is interested in knowing a bit of the history of infectious disease epidemiology, then this is probably a good place to start. So now, how do you actually model an epidemic? Right? So there are many different ways in which you can approach. Depending on your background, you might be a little bit inclined towards the physics approach, which is more or less a mechanistic approach. So, or if you are a statistician or a data scientist, you might have a totally different approach. I'll talk about that. But a mechanistic approach was one of the first or the pioneers in this field. The good thing about this approach is that it relies on hypothesis for causal mechanisms. So you actually try to understand the mechanisms behind something. So the mechanisms behind the disease progression, the spread of the disease. And typically, the parameters that you have here, they have a physical meaning. So it's easy to interpret the model, and it's very nice. On the other hand, the statistical approach, or nowadays it'll be like a data science approach, this would typically require large amounts of data for reliable predictions, and it's less mechanism based, but rather model fitting. So that's why it requires. But on the plus side, this has the ability to do proper uncertainty quantification. So this allows us to estimate uncertainty in our predictions. So when you have large amounts of data, you can build, whether or not it's a Bayesian framework, you can do uncertainty quantification in a principled fashion. So that's its. And these two approaches seem kind of orthogonal, but is it possible to utilize both of these these approaches in a way? And the answer to this question is, of course, yes. And whenever you ask a rhetorical question, most of the times the answer is yes. And yes, so I would like to convince you that this approach called dynamic survival analysis is actually a combination of these two methods. So you have a mechanistic component to it. You try and explain the underlying mechanisms there, and then it has a statistical component that allows you to do parameter inference. So this is kind of a broad picture of what this whole notion of dynamic survival analysis is. So what do we see here? So this picture tries to explain the multi-scale nature of infectious diseases. And what do I mean by different scales here, or by multiple scales? Well, on the left-hand side, let me see if I can, right here, so the left-hand side, you have this micro scale, which is the individual level scale. Okay, so this is how do you specify a model at that scale? Well, you write likelihoods for individual epidemic trajectories at this scale. On the right-hand side, what you see is the macro scale, which is also known as the ecological scale or population level scale. And what you do here is you write down ordinary or partial differential equations for the concentrations or proportions of infected individuals at the population level. Okay, so here we are trying to specify laws at the individual level, and here we forget about the individual, but we look at the entire population and then try and write ordinary or partial differential equations. How do we move from one scale to another? Well, this way is actually quite easy. So you have your individual level quantities here, likelihoods for individual trajectories. If you aggregate them together, if you put them together, if you sum all the infected individuals, then what you get is the compartment of infected individuals. And then if you take a large population limit, then you end up having this ordinary differential equations. So that's pretty easy. But what if I only have a description at the population level by means of ordinary and partial differential equation? How do I use those ODEs and PDEs to describe individual level trajectories? And that's where the survival dynamical systems, this notion of survival dynamic systems comes into play. Okay, so that's the big picture. So you have a description, you have a population level model. I want to use the population level model to do individual level analysis. Okay, so that's what this DSA is about. All right. So before I go into the details of this method, I would like to acknowledge some of the people who have contributed to this in some form or the other. Here's a partial list of people who did it. So the basic idea behind DSA was developed by Bosung Choi from Korea University and South Korea, Eben Kana and Greg Panda from the Ohio State University, and myself. And this was still done for the mass action model, meaning that anybody could meet with anybody else. And then you might have a network version of it. So that was developed in collaboration with Caleb Bastian from Princeton University, Yuhan Pan, a fantastic student at Ohio State University, Eben Kana and Greg Panda, and myself. And then we use this model for the COVID-19 pandemic, response to COVID-19 pandemic in the state of Ohio here in the US. And the response team constituted of many people across different departments. So Joe Tien from the math department, Evan and Greg and Elizabeth Root from geography, Mark Weir from sustainability, Susan White from the medical center, Christina Lizniski from the medical center, Courtney Hebert, Stan Lemeshaw, Harley Foster, and Johan Pan, again, fantastic students. So it was a truly interdisciplinary effort. And then we have our state partners, the governor's office, of course, but then Ohio Department of Health and Ohio Hospital Association. So as you can see, there's a lot of people have contributed to this, and I truly want to acknowledge their contributions. So just a caveat, the views that are expressed in this talk are solely mine, and they do not, of course, represent the official views of any of our state partners or the funding agencies. So all the mistakes that I make are mine, and all the good ideas are theirs. That's the thing. Okay, so now let's get into a little bit of mathematical details of this idea. And a good place to start would be the Kermack-McKendrick susceptible, infected, and removed model. So the SIR model that you've probably seen on television and heard about it maybe 1,000 times since COVID-19 started in India. Okay, so how does this work? So you have 3 compartments. So people are in 3 different compartments. The first compartment is called the susceptible compartment. So susceptible individuals are those who are susceptible to a particular infectious disease, and they become infected through contact with an infected individual. And then you have a particular given rate for that. And then infected individuals, they either infect others or at some point they get recovered. or removed. And then you have the recovered individuals who cannot be reinfected again. So there is no reinfection in the basic model. Okay, that's the idea. And now mathematically, at least in the classical form, how do you describe the dynamics of an SIR model? So you have three ordinary differential equations. ST is the proportion of susceptible individuals, IT is the proportion of infected individuals, RT is the proportion of recovered individuals. And then you have beta as the infection rate here. So you can say that, okay, the susceptible individuals, they actually recover or decay exponentially. If you just look at this equation here, and gamma is the recovery rate. So that's the basic model. If we look at a typical trajectory, so that's what you see on the right hand side here. So on x-axis you have t, which is a short form for time, and on y-axis you have the concentrations or the proportions of individuals in different compartments. The blue curve shows you the exponential decay in the number of susceptible individuals. The red curve is the proportion of infected individuals, which is going up, up, up. So you see an exponential phase, growth phase initially, and then it remains. So this is the peak. It reaches a peak, and then it starts going down. And the reason it starts going down is that one, a lot of infected individuals start recovering. So, and two, there are not many susceptible individuals left to actually infect. So that's why it goes up, reaches a peak, and then comes down. And then the green one is the recovered individuals, so which is supposed to just grow up. Okay. And then some basic ideas. One of the key ideas is the notion of basic reproduction number, which is the expected number of cases directly generated by one infectious case in a fully susceptible population. So if you have, let's say, a large class of or a room full of susceptible individuals, if you plant one infected individual, how many cases do you expect, additional cases, except for the first one? So that's the basic reproduction number. And then there's something called defective reproduction number that describes the number of cases generated in the current state of the population, which may include other infected individuals and recovered individuals. So both of those are very important quantities. And then if either of these two numbers is greater than 1, then you expect a large outbreak. So our goal would be to keep it as low as possible and preferably below 1. Okay, so that's if you are interested in public health, this is what you are after. And also, if you're government, this is what you want to achieve. And here's a link to a website which shows you for COVID-19 real-time effective reproduction numbers that you might want to check out later. All right, so now just moving on, we just learned what the Kermack-McKendrick model is, and you might have already noticed that this is a population level model, right? It prescribes the proportion of infected individuals. It doesn't talk about one particular infected individual. It says the total number of infected individuals in the population and the susceptible. So it's a micro model, but it's actually very easy to arrive at from a micro description, and that's what we'll try to do now. So that this notion of multi-scale dynamics is also emphasized. So we'll try to model at the micro scale now. Okay, so suppose there are n susceptible individuals and m infected individuals at the beginning. Okay, and then for each I is for individual, define this process SIT, which is 1 if he or still she is still susceptible at time t, 0 otherwise. It's just an indicator function that tells you whether or not a person is susceptible at time t. And then similarly define II and RI. And then for simplicity, we'll assume that everything is Markovian, meaning that all the inter-event times are exponentially distributed. That's just for simplicity. This also works for non-Markov models, but we'll only do the Markov model here, okay? All right, so how do I then write down? So this quantity, these are functions of time. They're stochastic processes. If you're familiar with statistics and probability theory, these are stochastic processes. How do I describe the trajectory equations for those stochastic processes? Well, this is how you can describe. So you are either susceptible at time 0. So this is the initial condition. And then you have many independent Poisson processes. So these are the Poisson processes, which starts at 0 and then moves by jump of sizes 1. So moves at 1 and then stays there, at least in this case. So this basically tells you that if you're susceptible initially, you remain susceptible for a while, and then at some point you get infected, and then this becomes 0. So if you start at 0, you become 1. If you start at 1, you become 0 at some point. And the same you can do for II and RI. So these are called the random time change representation of Poisson processes. So it's a fairly convenient way of writing down the trajectory equations. Okay, there's one more way to think about it, and that's called the Selke construction. And this is very crucial, and I want everyone to follow this idea, because this is really the key idea behind a dynamic survival analysis, which combines dynamical systems theory and survival analysis. So how does this work? So suppose we have a bunch of individuals, and to each individual we assign a threshold, which is distributed according to an exponential distribution with mean 1. And then we calculate the cumulative infection pressure, which is just the integral of, so remember, these are the indicators for individual infection, whether or not somebody was infected. So this is the cumulative infection pressure in the entire population. And then we say a susceptible person gets infected whenever the cumulative infection pressure exceeds his or her threshold. So that's the simplest possible description of the Selke construction. You just say, okay, everybody has a threshold, and whenever the infection pressure exceeds my threshold, I get infected. So pictorially, this is what it looks like. So on x-axis, you have time here, and on y-axis, I just ordered those thresholds starting from the smallest value up until to the largest value. And suppose we start with one single individual. So this cumulative infection pressure has a slope. So this is my curve, has a slope of just 1, or not just 1, actually beta by n. So the infection rate is going up and up and up. And at this point, let's say it reaches or exceeds the first threshold. So one more person gets infected now. So this is the first infection. And then now the number of infected individuals is 2. So this is now going up. So the slope increased now. So this is going up, up, up. And then at this point, somebody recovers. So now we are back to one single infected individual. So the slope decreases. And then let's say we cross the second threshold here. So it starts going up again. And then suppose there is a second recovery, and then it goes up, and then third, and so on. And then after the fourth recovery, here there is no more infected individual. So it just remains flat. So this epidemic dies out after 4 infections, new infections. Okay, so this is the Selke construction. This is fairly simple and very intuitive. Now, if we want to put it in a concrete mathematical form, this is what the Selke construction is all about. So it says the probability that an initially susceptible individual will remain susceptible or remain uninfected till time t is given by this quantity. Of course, conditional on the process, the history of the process. The probability that you will remain uninfected is the same as the probability that my cumulative infection pressure does not exceed my threshold, which is to say that my threshold is still larger than the infection pressure. That's given by just e to the power minus the cumulative infection pressure. I want you to remember and note that this is nothing but an exponential probability. Okay, so that's the key idea. Selke construction gives you an exponential probability of this. Now we'll see what to do with it. Okay, now how do we move from the micro description, where we had these individual trajectories, to the macro description? Well, if we just accumulate, as I said, it's very easy to move from micro to macro. So if we just accumulate all the susceptible individuals, all the infected individuals, and all the recovered individuals, then then we can again write down trajectory equations for those population level counts. Now we are no longer talking about individuals, we are now talking about population counts. We can write down trajectory equations using unit rate Poisson processes now. Okay, so this is following again random time change representation of Poisson processes. We get 3 equations. So these are stochastic equations now. The good thing about this approach is now that if I know that my population is large, so if I look at the scaled process, which is like instead of just looking at counts, if we look at the proportion of individuals, and if I let n go to infinity, n is my initial number of susceptibles. If I have a very large population, then I know that the scaled stochastic process actually converges to deterministic equations that satisfy this ordinary differential equation. And if you remember, this is the same as the Kermit-McKendrick ordinary differential equations. So that's nice. It's somehow compatible with the old classical theory. Now, what do I do, or what do we see here on the right-hand side? What I did here is I just tried to solve the set of equations partially. So ST I can write down in this exponential form, so e to the power minus beta integral of this quantity, and then IT I can again use change of variables and things like that. I can write it in this partial form, and then RT also this way. And there's a particular reason why I'm trying to do it this way. And the reason is, as soon as I write it as e to the power minus beta integral of proportion of this, you will realize that this quantity inside is nothing but the limit of the cumulative infection pressure, the Selke construction, right? So this probability e to the power minus this cumulative infection pressure was nothing but the survival probability, the probability of remaining susceptible till a time point t, right? So all of a sudden, this guy, which was describing the proportion of susceptible individuals, is also describing a probability of remaining susceptible, right? So that's very important. Okay, so I'm putting a star here. IT, if I look at it, so forget about this initial condition, but if you look at this guy, if this is a survival function, minus ST dot is a probability density function. And this guy is anywhere density of exponential distribution. So does this form look familiar to you? I mean, if you have an engineering background, you will immediately realize that this is just a convolution of 2 probability density functions, which, if you have again some background in statistics, would know that describes the probability density of the sum of 2 independent random variables. So this now describes then a density function because it's a convolution of 2 densities. Okay, and RT is just a cumulative hazard function. So if I just now put things pictorially, now going back to these typical trajectories thing, on x-axis we have time, on y-axis we have concentration stills or proportion of individuals. You have the S curve, but this is not just proportion anymore, as we just saw that this is also a survival function. So survival function is typically this quantity whenever you have x greater than equal to t. These kind of quantities are called survival functions. So 1 minus cumulative distribution function. The I curve is also describing now a density, not just a count of infected individuals, and this is a cumulative hazard. So that's the thing. So what you have just discovered is that the dynamical system that we were talking about here, so this dynamical system actually also describes probability distributions. Okay, so sorry. So that's the basic idea behind dynamical survival analysis. Okay, so you have you have a dynamical systems that you turn into probabilistic quantities. So here's the link to the paper that it's an open source paper. It's an open access paper, so you can have a look at it. That describes this idea in a very simple form. And here's a link to the GitHub site where you can find a Python implementation of these ideas. So both of these are available. You're free to use it on any data you want for COVID-19 for India. I think I actually started doing that some time ago, but then I myself was so busy with the COVID-19 response in the state of Ohio, I couldn't really pursue it any further. But you are free to use it and see if it's helpful. All right, so we briefly described how you can extract probabilistic quantities from dynamical systems. Now we'll talk about the statistical benefits. Like, what's the big deal about it? Okay, so it's good to know, but what do we do with it? Well, the benefit is that the individual trajectories are kind of independent in the limit, which means, so this is also called the mean field independence or propagation of chaos. But this has a huge implication in data science. So which means that you can write down likelihood functions that are in a product form. So very easy to compute and very efficient algorithms you can devise. So the big thing is that you can write down an SDS likelihood function that's just based on transfer times instead of population counts, because now you have, as you have seen, that this dynamical system describes probability distributions of times of infection, right? So how long you remain susceptible is basically how long it takes for you to move from the susceptible compartment to the infection compartments. So times of infection. So you can write down a likelihood function based on transfer times instead of population counts. Why is this important? This is important because population counts, we never know. Sometimes you don't trust the government data. Sometimes you know that, okay, this is highly dependent on how many testing you are doing. So you hardly have any clue about the prevalence of a disease. So you getting accurate population counts is nearly impossible in any country on this planet Earth. But if you have a random sample of individuals and you know their transfer times, this is just enough for this whole approach. So that's the big thing. Okay. So it has a nice. This is possible because of a binomial random measure, but this gets into probabilistic technicalities. So I'll not go into the details of this thing, but the underlying mechanism is given by a random measure here. But I'm happy to talk about it if you have any questions, but otherwise I'll just skip it for now. So here's again a cartoon depiction of this idea. So suppose you have this big population and you can't potentially keep track of everyone, but you can probably keep track of a random sample of individuals, right? So that's what we call a human sentinel network. So you have these individuals, you have the whole population, and then this is my random sample. And then they change color. So if they're blue, they are still susceptible, and then they turn red, they're infected, and then they turn green, they are susceptible. So what you do is you just pick a random sample of individuals, keep track of when they get infected and when they get recovered. And that is sufficient for your analysis. You don't have to keep track of the entire population. Okay. So, all right, let's now try and see how the whole model would work on a network, because as we all know, we probably don't live in a mass action setup. So we are not gas molecules. We don't just randomly move around. We live on a network, and we can only infect, let's say, a handful of people, not the entire population. Not the entire city of Calcutta is susceptible to one single individual, right? So in order to build a model on the network, we need a model for the network itself, right? And one convenient model is known as the configuration model network. Okay, so configuration model networks are, it's a random graph, and it's very convenient analytically because you can either provide a degree sequence for your graph, or you can draw your graphs from a probability distribution. Okay, so this is the feature of configuration model. So how does this work? So kind of like this cartoon picture here. So you have your vertices and you have some random degrees. So these are half edges, and none of them are paired. So what you do now is you take two of those half edges uniformly at random, match them up, and that forms an edge. So kind of like what you see here. Okay, and you continue this process up until you have exhausted all the half edges. So there is no more half edge, and that's when the graph is completed. Okay, so like this. So that's my configuration model network. Now, how do I run the epidemic process on this network? So I think there's a question there. Okay, yeah, thank you. Yeah, please feel free to interrupt me if you have any questions. I'm trying to go slow and keep it at a very basic level, but if you are curious to know the mathematical details, I'll be happy to share more details. Anyway, so we have this this graph. How do we play the SIR process, for instance? Okay, so we do that by coloring our vertices. So we say that, okay, the blue colored vertices are now susceptible, the red colored vertices are infected, and green are recovered. Okay, so we say that, okay, I have this graph here. Some of the vertices are red at the beginning, some are blue, some are green. And the red vertices, the infected ones, they try to infect their neighbors. So this guy was initially, this is initially infected. He infects this guy. And then as soon as he infects, he gets infected, he infects somebody else, and so on. And then this is how the disease progresses. So that's one possible construction. The other construction is to say that, okay, I don't have the graph a priori, but what I have is I have the degrees and I have initial statuses, and then I'll form the graph dynamically as the disease progresses. Okay, so I have the same color scheme here. So susceptible, infected, and recovered. The red ones, they are the infected ones. What they do is they pick one of their edges, free edges, and then one more edge from the collection of all possible edges in the graph, and then pair. So it forms a graph. And now if that particular edge belongs to a susceptible vertex, then he turns infected. So kind of like this is infected. So let's say he chooses, this guy chose this one and this one. So now we form an edge here. And this, since this guy was initially susceptible, he turns infected. And then at some point, the infected vertices, they also turn green. So this is a dynamic construction of the graph. And from a probabilistic point of view, both of these constructions are actually equivalent in the sense that they give you the same probability laws for the quantities that you are interested in. Okay. So now that's enough about the premise. What do we need mathematically? So mathematically, we need a few things. The first thing is the degree distribution. So let's say pk is the probability that you will have degree k, and then this guy is the probability generating function, that's the definition of it, and mu is the average degree in your vertex, in your graph. And then I need a hazard for the infection, and then I need a hazard for the recovery. So this is infectious period, so beta and gamma. This is exactly similar to gamma. And then now, in order to account for social distancing or quarantine or lockdown, I have one more parameter, which is called delta. So how does this work? So this works, so the infected individuals, when they get infected, they try and drop their edges. So they try to dissociate from the graph. So they try to disconnect from their individuals. So I have this one more parameter that's accounting for social distancing. And this is actually new. So this is something that we had to modify after COVID-19 lockdowns were in place. So we had to come up with this this thing. Okay. Now I'm hiding all the maths behind and just showing you the final result. So let's say if we assume my degree distribution is Poisson, then, and if I take a large graph limit, so that's again a law of large numbers kind of limit, then the final proportion of susceptible individuals in the graph is given by this equation. So you can reduce the whole thing into one single equation with these revised parameters. So why do we have revised parameters? Well, precisely because the parameters themselves are no longer identifiable. So for instance, the degree of the graph and the infection rate. So if you know that there is a lot of infection going on, so there are two possibilities, right? You might say, okay, the the graph has very large degree. So whenever somebody gets infected, he can potentially infect many people. Or you might say, okay, the degree is not that large, but the infection rate is very high. So he's infecting very quickly the infected individuals. So you can have both of these. So, and that is precisely because what matters is the product of the average degree and the infection rate. And there is some identifiability issue. So that's why we have to reparameterize the model so that we can identify the system given data. But this is basically what you get. And I'll be happy to show you how you get these limits and everything, but that's a different mathematical discussion. Yeah. Okay, so let's move on. Okay, so now we have the mathematical pieces in place, and let's try and apply this method to COVID-19 pandemic data. We actually applied this to the US data, to India, to South Korea, and many other places, and did analysis, plenty of analysis with it. But I'll show you one particular case study that we did for the state of Ohio, actually, the state government of Ohio. So as I mentioned, in February, I was still in France, and then as soon as I came back, I think COVID-19 already, started to appear in the US and in Ohio. So we started discussing with our state government that we need to do something. So this is kind of the situation. So as you can see, this is on March 19th. This is the data that we had, and it kind of looks like, okay, this is going up. So this is kind of an exponential phase. The last few days is always testing backlog and so on. But this is like a nice textbook example of an exponential growth. So the government asked, okay, what do you think? So we had to come up with some predictions, and this is what we did back in March. So we were still here, I think March 19th or something like that, and we had data till this, and then we applied this method to identify the model, and then we said, okay, if we do impose lockdown and everything, then we will be somewhere here around 200,000 cases here, and then if we don't impose lockdown, meaning that this delta parameter that I initially introduced is 0, so people don't practice social distancing norms, then this could be really catastrophic, and then we could have as many as 350,000 cases very quickly. So that's what we did like back in March. Then as we collected more and more data, what initially looked like an exponential growth, this was going up, but then something happened. It's kind of like this. And then we were puzzled, okay, what happened here? Why is it like this? But anyway, if I have to fit the model now, so now it's no longer an exponential growth, but it's rather something that grows exponentially and then maybe linearly, right? So we needed to revise our estimates. So now from more than 200K, we were back to 175K. We had to revise it a little bit, and we were still not sure whether this phase was actually real or this is actually due to some sort of testing delay or something like that. So long story short, we had to revise our models. Now again, this is data till mid-April. As you can see, we have initial exponential growth, but then there's this plenty of plateauing thing going on. So it looks like almost a straight line here. So instead of an exponential growth, what we see here is, sorry, yeah, what we see here is a linear growth instead of an exponential growth. So we had to take that into account, and then we had to drastically reduce our predictions. So as you can see, this is the linear growth phase here. So we're trying to fit a model that has an initial exponential growth, but we were talking about thousands here, not in 200,000 or 100,000, so 30, something like that. So now here's how COVID-19 actually shaped this thing. Some timeline of social distancing measures. What happened here in the state of Ohio? So you have on March 5th, spectators were first prohibited from this Arnold Sports Festival. That it was a good thing that they did, because otherwise it would have been catastrophic. Then Ohio declared a state of emergency on March 9th. And then March 12th, all large gatherings were prohibited, and then bars and restaurants were closed, and statewide school closure was done. And then there was barber shops and beauty salons were closed on March 18. So, and March 23rd was finally the stay at home, the lockdown was imposed. And all of those had this huge impact on the epidemic curve. So traditionally, if you study Kermit-McKendrick kind of models, you know that you have a nice exponential growth phase and then it decays. But what social distancing did, or these orders did, they had an exponential growth, and then it kind of broke down the exponential growth phase into a linear or sublinear or sub-exponential kind of phase. And this phenomenon is not just an Ohio thing; it happened at many different places. But anyway, so that's the timeline that broke down, the epidemic in the state of Ohio quite successfully, at least initially. What do we stand now? Now, okay, we were under lockdown for a fairly long period of time, and then we had to reopen, and then reopen the state as well as university campus and everything. And then this has been going up again. So we saw another exponential growth phase here. So what you see here, and then the predictions are again now in 160,000 cases in total by the end of November. And this solid red curve, I don't know if you can see, this one is actually the actual data. So as you can see, the model, the dynamic survival analysis model, is actually tracking the epidemic fairly accurately as compared to many other models. So this is the crux of it, and here's some bottom line. Yeah, as I mentioned, we applied this method to a number of other countries with a reasonable success initially, and not so much later on because of this plateauing thing. But we also had to, incorporate change points into the model, and that allowed us to fit even better models. But I don't want to go into the technical details of those things. I want to keep it fairly general and simple. But the bottom line is, as we developed this this method, we had to make a lot of tweaks, and COVID-19 basically played a big role in also developing this methodology. This plateauing seems to be common in many places. It happened in Italy, it happened in Germany, in South Korea, in the US. I mean, I don't know if you have been following the curve at US national level, and that's a very weird curve. So yeah, so this seems to be quite general, but the bottom line is that social distancing works. So even for India, I do hope that people practice social distancing, and the recovery rates and the mortality rates are good signs. So, but still, I mean, we don't need to be afraid, but we should be cautious. We should be concerned. In terms of science, the dynamic survival analysis provides a principled approach to parameter inference and uncertainty quantifications. It in a way combines survival analysis and dynamical systems theory. This has worked in Ohio and US and at many other places. So please have a look at the GitHub site and the paper. The paper is open access. Everything is open. The bad news is that there are still plenty of unknowns. There's no mechanistic understanding of this plateauing. I mean, we know that this is caused by, let's say, lockdowns and things like that, but it's it could be more nuanced. It could be more subtle than that. This explanation works for Ohio, but I'm not sure if that is the only possible explanation, and there could be something more than that. The effect of seasonality is not known, right? There have been a lot of speculative studies, but those are all, yeah, if you put it bluntly, are all somewhat speculative. So, and then there is a lot of biological unknowns. There are many puzzling peculiarities about COVID-19 and the optimal control of COVID-19. The model that I described to you today is the Markov model. Right? Everything is exponential and things like that. You have a single parameter to fit. It was a constant numbers, but this could be easily extended to non-Markovian model. We have done that. And then in the non-Markovian setting, you can actually turn those non-Markovian models into Markov models, but those Markov models will be more abstract. So they will be Banach space valued Markov processes, and then you can use standard limit theory for measure valued processes to do a similar kind of analysis in that generality. But the bottom line is this works even in the non-Markovian setting. You can account for differential susceptibility, account for age of infection, and write down partial differential equations. You can account for heterogeneity in the population, gender, age, and other kind of comorbidities and covariates. All of those things could be accounted for in a mechanistic way into your model and then used for statistical purposes. So that's what I was talking about, that this dynamical systems dynamical survival analysis approach is a combination of this mechanistic approach as well as the statistical approach. So that's the bottom line. So with that, I would like to acknowledge funding. A lot of people have have provided funding through various mechanisms: the National Science Foundation, the National Institutes of Health, the Mathematical Biosciences Institute, and the Ohio State's President's Postdoctoral Scholars Program course, and the slides template from Hakim Al-Hattab. So with that, I think my time is probably up. So I would like to stop here and would love to take your questions, and would open the floor for discussions and and Q&A in general. Thank you so much.
Good evening, sir.
Good evening.
Sir, with your permission, may I ask you some questions related to this? Actually, I'm also working on the dynamical system. Actually, we were working on some network model and all, and there what we found, maybe due to some parameter adjustment, we got something, some erroneous result or something. I don't know. Actually, this network model shows that if we lift the that means if we start that unlocking process, then the system, that means the infection get up to its saturated level till that means it's earlier than if there is prolong that if we prolong the lockdown system. So is there some problem with that or network model, or it is due to this maybe I don't know. We are getting something like that.
What kind of network model are you using? And so it depends a lot on what goes into it.
Sir, we just worked on some small population, means we are working on the West Bengal perspective. And there we have selected some region where the population concentration was there more, and we have considered the center place to be Kolkata, and the neighboring districts whichever are connected through bus or train lines. So there we have considered that kind of network model, that before and after lockdown, what can be the possible thing, or what will be the possible thing.
Is it like you have a, so is it like a deterministic model, but you have like patches? So is it a patch model or population model?
Kind of patchy model, but thing is that we have just SIR network model that we have we have considered, and there we have connected. We have considered that people are going from moving from one district to another district, and they are coming back again. So this kind of model with some rate, we have considered that we have hypothetically we have considered some rate, not exactly hypothetical, but some statistical data from railway we got. So
Yes.
therefore we have started computing that, but there we have seen that this unlocking is far better than lockdown. So so that because if we unlock, then the disease get its saturated level are faster than the lockdown, and the early the disease reaches its saturation level, the early it will be it is reducing, since in Indians perspective the mortality rate is a bit lesser, or the reproduction number is also lesser. So what may be the possible reason behind that?
If you don't have a lockdown, then the disease will, yeah, I mean, with a lockdown, you're basically delaying the peak, right? I mean, that's the basic idea. So I think that's quite intuitive. And that's true whether or not you have a network model. I mean, regardless of how you specify the network there, you're going to delay the, but then the question, crucial question is how large is the peak, right? And the with the given mortality rate, can you afford to have lose those many people, right? I think those are the more important questions. In terms of, let's say, the specific parameters, that I don't know if you have how you have estimated those things, but
Okay.
one suggestion that I might offer is a try and validate using different methods. I think to see whether the conclusions that you are getting are robust enough. Uh,
Okay. Okay. Okay.
and you know, for what range of parameters, because all of these things, I mean, many times, especially in infectious disease epidemiology and in this current era of COVID-19, I mean, there have been like so many different models, like thousands of them, and
Yeah.
then with different choices of the parameters, you can generate any possible outcome you want. It's I mean, uh, you can generate anything you want. So
Okay.
the question is the kind of conclusions that you're getting, how robust those conclusions are if you moves a little bit away from, if you perturb your model a little bit, right? And so the question is, if you choose a different model, do you still get a similar conclusion about your system, right? So the thing that it's far better to lift the lockdown than to do this. If that's your main conclusion, does
Yeah.
this, still hold true if you change your model a little bit? Okay.
Okay. Okay.
I think
Okay.
that's something that we should. I mean, I'm advocating here dynamical systems approach, but I would also advocate like always and always and always compare different models and see how robust those things are. Don't get married to one particular method. I mean, we should
Okay.
get married to the science in general and to logic, but not to one particular method, and see how robust our conclusions are from a scientific perspective, meaning that if I change my parameters, for what range of parameter values does this statement hold true, and things like that. So yeah, but in general, as I mentioned, I mean, like if you have a lockdown, then you're basically delaying the peak, and as well as potentially lowering the peak. If you don't have a lockdown, you will
Yeah.
reach the peak earlier. So I showed you this picture, right? Maybe I can go back to this picture again. Initial. So this is what we started with here. Okay. Um,
Okay.
so this is the cumulative curve. If you don't have lockdown, this is the curve that I will see. So we reach
Mhm.
saturation. I mean, we started in March, and if we didn't
Mhm.
do anything, we would reach saturation by April, right?
Okay. Mhm.
If we do have lockdown, then this was saying that okay, we will see saturation in mid-May or mid or early June or something like that. So the question is, we were buying time to prepare our healthcare system to deal with this situation, right? And this kind of, I mean, maybe the numbers would be different, but this kind of behavior is quite, I mean, intuitive. So even if I change the model from this network model to something else, to a mass action model, something like, we will get similar curves. Maybe the numbers, I mean, on the y-axis will be different, because of different parameter choices, something like that. But this is in general true. Now the question is, can we afford to reach the peak as early as April?
Okay.
And of course, you have to then take into account the mortality rate and the capacity of the healthcare system. Those are the two crucial questions. So for us, it was very important that we delay it as much as possible, so that we can equip our hospital, or let the hospitals prepare,
The medical facilities and all, right?
Yeah, exactly. So I think we have to do the same thing for West Bengal and for India. Like,
Okay.
if I get a particular type of conclusion, I would try and move away from that particular model and see if I use a different model, a different kind of setup, do I still get a similar conclusion? I mean, it may not be the exactly same, but at least qualitatively, if they are the same. So if the conclusions are robust enough, and then there are other considerations like, can we really afford to reach peak much earlier and overburden or overwhelm the hospital and things like that. And then what is the age distribution? Because for COVID-19, we know that this is very much dependent on age and many different covariates. So I think, yeah, that's a fantastic point that you raised, actually. So yeah.
Okay. Thank you so much, sir. Thank you.
Modeling
Thank you so
talk.
much.
Yeah, you're welcome. Yeah, this is a modeling talk, but at the same time, I mean, science is much more than a model. So,
Yeah. Sure. Okay.
First, I would like to thank Dr. Wasiur Khuda Bukhsh, sir. He's from the Ohio State University. Really, already it is in the chat box that it is a nice and very informative session on the dynamic survival analysis of epidemics and how the COVID-19 had shaped it. I am really very thankful to Professor Khuda Bukhsh that we gather a lot of information over here, like the social distancing parameter, the parameter estimation, like the cumulative infections on March, how the social distancing has been worked onto that. It's a real nice information we gathered, and I want to mention that he has worked on in the November. It might be what I suppose that it is 1.4 million, probably in the USA record. That is also 1.4 million, am I supposed? That is also very informative, the data. A lot of work can be done on that, like the flattening, the effect of the seasonality. Anybody can work on that also, and that the data is also very informative. So, I'm really very thankful to Professor Khuda Bukhsh that for these informative sessions. I also thanks the organizing team, the whole organizing committee of the electrical department and the department of CSE, Global Institute of Science and Technology, whole IKEA team, the top management personals, and the principal of GIST, and whole IKEA team. Thank you to all of you, for the participants and everybody. Thank you to all of you. Good night to anybody.
Thank you,
everybody.
Thank you, Jyoti sir, for a nice speech. So now is time to go. Thank you again, Dr. Khuda Bukhsh sir.
Thank you so much for inviting me. It was a real pleasure.
Okay.
Okay. Bye-bye.
Thank you.